I'll ask Maurizio to come up to the stand, please.
I'll try to be quick, and we're reaching the level of fatigue here. And also, I think by now we are all a little bit more informed and all significantly more confused. But that's good, because that's the reality of biology. So what I wanted to flesh out very, very quickly, very briefly this afternoon is this flagship project that I'm leading at the Botanic Gardens. And it's a project that is directed exactly at these kind of issues. We do not have information to support our restoration goals. So how do we go about it? So just to quickly summarize, we talked a lot about this today, so I don't want to waste much time, but let's not forget that the main objective, the main aim of ecological restoration projects should be to re-establish self-sustaining population that will last the test of time. So it's not just purely of recreating what we imagined was there before, but it's about recreating something that will not need our help forever, and something that will be able to deal with changes, the normal changes that occur through normal ecosystems. And for that to be possible, obviously increasing diversity, increasing fitness, and planning properly is critical. So with that in mind, and also, actually, let me just go back to this because it's important. As we've seen, it's important to have an understanding and have an idea on how to develop frameworks on maximizing this long-term viability. And we've seen this model X amount of times, and they're fantastic models. The issue with that is that we do not have the empirical data to support those models so far, or we have it for a few species. I mean, we had a fantastic example before from Rebecca, but the reality is for most species, we don't have the necessary information. It's great to think about doing climate-adjusted provenancings, but what's local, what's not local, what's the climate going to do? We need to have that information. And so far, we haven't been able to do that because gathering that information is complex. There are lots of different factors that are involved on the optimal self-sustainability of a population. We need to understand about not only genetic diversity, but the spatial composition across the distribution of the species, the interaction with the other species, temporal factors. How does it change through time? Why? We need to understand about climate. We need to understand all the things and how all those things interact with each other. It's complex, it's costly, and we have tended to put it in the too hard basket for that reason. But the point I'm trying to make here is that it doesn't necessarily need to be that way. These days, there have been so many advances, technological, analytical, interpretational, that we should be able to obtain baseline information of that kind for a large number of species. And certainly that's what Restore and Renew, that's what this project is about. The other important consideration from a scientific point of view about obtaining and providing this information is that there is always an economy of scale. Obviously, if you're working with one species at the time, you can get fantastic information, as we've seen from Rebecca, but that's been a whole project for 3 years as a PhD project. If you start working on hundreds of species at the same time, certainly you can reduce the costs, you can reduce the labor involved, and you can really make the most of economy of scales. Plus, the other important thing about working with lots and lots of species, of course, we will be then in a much better position to generalize for the species for which we don't have data. Now, generalization, as we've seen over and over throughout this meeting today, is not really possible because every species has got different or specific conditions that we really don't have necessary information to interpret. So, the objective of Restore and Renew, as this paragraph says, is to really provide a tool to land managers and restoration practitioners that will help them decision-making through their restoration processes. And more importantly, as I was mentioning before, will also provide the baseline data to not only do restoration processes, but set experimental trials. We talked a lot about experimental trials, but we still need a minimal level of information. And also the information necessary to then monitor success of those experimental trials or restoration practices in general. So it's really about not telling you what's right or wrong, but giving you the power to actually test some of the questions that you're interested in, that we're all interested in. And I think this is just going back to what I just said. And so just to explain how we are planning to do this is to do all the research and then provide that research. Because again, often it happens that fascinating research is done, but then it's hidden away in scientific papers that people cannot access or cannot easily interpret. So what we want to do is do all this research and then provide it into an easy to access and easy to interpret website. And that doesn't mean there won't be other research and scientific papers in the background, but there will be an output that is easy to use. And our objective is to work on about 250 species. The list keeps on changing, but this all started first with a survey of practitioners in New South Wales, where we asked them, what are you interested in? What are the type of questions that you would like us to answer? And more importantly, what are the species that you commonly use? Don't look at that list of species, but this is just an example. And from that list, then we got a team of practitioners and ecologists together to handle it and change it a bit, and we've got our target species of 200 plus species. So how do we work? The objective is to get genetic, environmental, and ecological data across all those 200 species. So let me just go through very quickly the process on how we go about this. We start by developing environmental niche models that take into account current, past, and future conditions. Ari spoke about mechanistic models as well. We're moving towards there, but obviously getting the information, mechanistic information, physiological information necessary for those models is more complex, so that's a slower process and a secondary process. Now, earlier on, I was talking about the importance of getting multiple layers of information from the genetic data. And this is why we pair it with different type of environmental models. So obviously the current models we use to understand relationship and association with climate and edaphic factors. And we also use to help us with our sampling strategy, and I'll talk about that in a second. The past models, the glacial models, help us put the genetic data into a temporal context. Can we interpret some of the genetic patterns that we see with changes that have occurred through times? And that's important in many ways, not only because it gives us that answer, but it also gives us an understanding of how responsive a species can be to change. And then obviously the future models are the ones that we try to relate to predictive scenarios. Once we have that information, and without going into details, we sample extensively through the species. We tend to focus on sampling from as many sites as possible, rather than as many individuals as possible. Usually we sample from about 30 to 40 populations, depending on the distribution of the species. And then we use genetic tools that are fairly modern and advanced. So you've all heard about human genome and all these kind of projects. We can now get fairly quickly and fairly easily and fairly cheaply whole genome analysis across all those species. And that's very important for a number of reasons, because that's one of the reasons why we can sample the way we sample, but we can get many, many, many layers of information from that. So we can then, based on this information, based on the distribution of species and on the environmental models that I was talking about before, we can then do representative sampling across the species and obtain lots and lots of genetic data from there. Then, from there, we can then derive site-specific information on relatedness, on genetic diversity, on association with climatic factors, etc., all the kind of things that I was talking about. And one of the important things that we want to do, because we're dealing with so many different species, we need to identify analytical pipelines, analytical processes that are fairly quick and fairly informative. And so, without getting into details, we settled in one specific approach which really helps us use all those different layers of information at the same time and gives us useful outputs. And I'll show you a couple examples of the type of outputs that we get. The other important thing to consider here is that because we are doing this process at such a large scale, we will have, or we already have, a whole lot of data sets that will be directly comparable. So we'll have all sorts of information that we can compare to each other, all sorts of data sets we compare to each other and ask questions of across landscapes. We can ask questions about vegetation groups. We can ask questions about taxonomic groups. We can ask questions about climatic groups, functional groups, etc., etc. So let me give you a couple of quick examples on the type of information that comes out of that. And this is a simple, very simple scenario where we are looking at genetic differentiation, genetic connectivity across the landscape. How do we use that information to define local genetic neighborhoods? Because we've seen a lot of the scenarios, a lot of those models that we've talked about before are based on local, non-local, this and that. But how do we define local and non-local? We've seen it before, 10 kilometers, 100 kilometers. People have all sorts of different opinion on what local is or isn't, and they have all sorts of different opinions because it varies across species. So what we want to do here, what we do here is let the empirical data, let the data we collected tell us what's local and non-local. So we feed all the genetic data that we have through a model, and then we let that model assess how genetic differentiation is distributed across the landscape. We do a lot of validation and verification to make sure that it's close to real data. And what that means is when, for any point across the distribution of the species, we can identify what the relatedness of any other population within the distribution of the species is to that point. So you know what is related and how it is related to that particular point there. And from there, it's easy enough to then do a cutoff point based on a certain amount of diversity that you consider local and identify the area of local diversity, which is easily transferable into a visual. So that's the model output, and that's the visual version of that model there. So I didn't mention before, but this, this particular example is Neolitze de Albara, which is a small tree in wet sclerophyll rainforest type of habitat. It's got fleshy fruit. It's easily dispersed, a lot of connectivity across the whole distribution of the species. This is one of the species where relatedness decreases pretty much evenly with space. And so when you do those models, you get a pretty even area, circular area of relatedness, which makes perfect sense in that model. And so once you transfer to that, obviously, from a practical point of view, once you transfer that information into the web, you can actually put a lot of information there. So it's not only about the neighborhood, but you probably can't see, but you can actually put the points where we know that the species occurred, and then there is a pinkish, brownish coloration as well, and that tells you about the environmental suitability of that particular area in relation to the distribution of the species. And of course, we can change that with future models, etc., etc. So a very practical output where you've clicked on your point, you've selected your species, you click where you want to do your restoration, and you get the information there. And hopefully when we do get the website is not up yet, when we do get the website, it will be possible to transfer it to an app type of thing where you can follow where your eyes, you drive along and make sure that you can do your collection at the right spots. I just want to show another quick example because, of course, a situation like this, what we call isolation by distance, where the more populations are geographically spaced, the more their genetic differentiated, doesn't always happen. So you don't always get the kind of circular model. So the other example that I want to use is that of Banksia ricifolia, where we have two very differentiated genetically, environmentally, and ecological groups. And we can bring all this information into the model, and what this is showing, what I wanted to show here is that if you were to pick a site close to where the transition between those two very genetically differentiated groups occurs, the model will identify and will respond by telling you that if you go over, you can't move too much in the direction where the transition occurs, you need to collect more on the other side. So it works really well. And as I was saying, we can put many, many other layers of information into it. There is one additional thing that we're working on. So it's not only about defining those neighborhoods of genetic identity, but it's also, one of the important things I think that should be coming across from the data, the amount of genetic diversity is also important. And so one of the things that we want to do and provide practitioners with is some sort of idea of that balance between the amount of effort and the amount of information that you will get. So if I collect from that many trees, how much more genetic diversity will I obtain? And also, how will that change if I change scenarios? So the scenarios that we saw. So before, if I collect local only, or if I'm doing mixed scenarios, et cetera, et cetera. And so we're still working on this, but to cut a long story short, this is, again, as you would expect, this is a preliminary trial, but for a what this is telling us is for a species such as Neolissa delbara with that great genetic connectivity across the landscape, really adding many, many more individuals doesn't make much difference. And moving away from local does not add much genetic differentiation. So you can see it on X amount of individual from that particular scenario, and there will be more than enough. Again, this is not prescriptive, it's just letting you know how to maximize outcome from minimum effort. And as I was saying before, this is the information at species level, but obviously, once we will have all that information across many different groups, across the whole 250 or how many species we end up doing, we will be able to do much better generalization. So we will notice that there are patterns, and we already know because we have done quite a few species and we can see the patterns. There are specific patterns across specific functional groups. Again, ease of dispersal being one that is quite important. We can see if there are similarities across taxonomic groups, et cetera, et cetera. We can also use this particular approach to define and support the establishment of seed production areas. So do you want a seed production area that focuses on local material only? This is what where you should collect from and how many individuals you should include in your seed production area. Do you want to do a mixed seed production area? This is what you should do. More importantly, there's also many, many outcomes you can imagine from a scientific point of view, especially, but also from a land management and biodiversity management point of view, when we will have all that information across all those species sampled, analyzed, and interpreted in the same way, we will have some very, very powerful tools for understanding the distribution of genetic diversity and the interaction, the association between this distribution of biodiversity and a range of factors. This is just an example of some preliminary work that we're doing with 12 rainforest species, and what this is showing, this is across the landscape, where the center of diversity, so genic, if you want, biodiversity rather than species biodiversity. And the two don't always correspond, which is quite exciting. So far, just concluding, so far we've done about 30 species. We've collected 10,000 samples. We're hoping the website will go up in sometime early next year. There's a domain there, but there's nothing there, so don't just go and have a look yet. And one of the things that we're really interested in, obviously, is expand the collaboration. Species don't recognize political borders, so we started to develop some collaborations here in Victoria and in Queensland, and we hope to develop that much more. And I'll just leave it by mentioning our sponsors. This is a fully sponsored funded fully by sponsorship and donation. It's not the kind of thing, unfortunately, that you can get scientific grants for. And the team. Thank you.